Welcome back to the Lowdown on Physics. This is Screencast number 2 in the series on radioactivity for Unit 1 Physics. Today we'll be looking at radioactive decay. In any nuclear reaction, including radioactive decay, there are two laws of conservation that we must always obey. That's the law of total mass and energy, and that is that the sum of the mass numbers must remain unchanged. So the numbers on the left-hand side for the masses must equal the amount of, or the sum of the masses on the right-hand side. And also the sums of the atomic numbers must remain unchanged. So if we look at a nuclear reaction here, we've got some element X and it decays to some element Y, giving off some piece of decayed atomic substance, whether that be, alpha particle, beta particle, or gamma radiation, or whatever it is. The sums of our masses, written at the top, and our charges at the bottom must always add and be equal. So the left hand side, A must add to the sum of these two here, and for our charges then M must equal N plus O. So let's consider alpha decay. First up, let's have a look at a uranium atom. So we've got a mass of 238, charge of 92. It decays, giving off 234 and 90, plus what is the equivalent of a helium nuclide. This is alpha radiation, plus some energy in the process of that decay. So if we check conservation of mass, we've got 92 down to 90, so it's lost 2 protons, and we've lost a total mass of 4, so it must carry a mass of 4 there. If we look at that diagrammatically, we've got our nuclide for uranium. It decays, giving off that alpha radiation. So remember that this is something that just happens spontaneously. It just can't be predicted when it's going to happen, and in the process it changes into a completely different element. So most of the energy released is in the form of kinetic energy, so we're moving maybe 10% the speed of light as it's ejected, and this is the form of radiation that happens in heavy nuclei. So your lighter elements aren't going to undergo this form of decay. Now if we have a look at beta radiation or beta decay, example here is bismuth, you'll notice that it actually increases in charge. Mass stays the same, giving off 0 and -1. So the -1 would suggest that we're actually decaying and producing an electron, giving off an electron. So there's a change in charge, no change in mass. Where does the extra charge come from? Effectively what's happening is one of the neutrons is changing into a proton in order for the atom to attempt to become more stable. So this usually occurs in nuclei where there's an imbalance of neutrons and protons. So if we look at that diagrammatically, here we've got a H3 atom moving, and that becomes a helium-3 with the extra protons. So remember, the protons determine what type of atom it is. So it's an isotope of hydrogen, which is tritium in this case, and we have helium because of the 2 protons there, and an electron is ejected as beta radiation. In the case where we've got too many protons, we could have positive beta radiation decay occurring. So here we've got an isotope of nitrogen. It decays and it gives off what we call a positron. So it's effectively going to be the reverse, a proton spontaneously changing into a neutron, and really the properties are the same except for the charge. So instead of being a negative beta, it's just positive, but the properties are effectively the same. So if we look at that diagrammatically, here we've got our nitrogen, it decays, and we see that this proton here has now become a neutron, ejecting a positron. Now for gamma decay. Generally this is something that happens after we've had alpha radiation or beta radiation or some series of decays, and basically the daughter nucleus is holding an excess of energy. So what's really occurring is that you'll see there's no change in mass or charge. What's really effectively happening is there's a rearrangement of the nuclide. It rearranges itself to a more stable scenario or structure and gives off gamma radiation, the excess energy that it no longer needs. So you can see here we've got an example. We've got strontium-90 decaying, and given the equation, and we said the question is to determine what X is. So look at the atomic numbers, the mass numbers, and then based on that work out what type of decay is occurring, obviously plus gamma radiation. So in order to solve this, we need to look at the atomic and the mass numbers. So for gamma rays they're both 0, so that plays no part on it, so we can look at balancing and finding the mass and atomic numbers for X. Now in that equation the mass number will be 0, the atomic number must go down by 1. So therefore if there's 0 mass and a negative charge, it must be an electron, and therefore we must have beta decay. Example 2, we've got iodine 131. It's a radioisotope used for treatment, blah blah blah. Let's get down to the good stuff. So firstly, we're bombarded with neutrons inside the core, and we get a formation of an unstable isotope and giving off a gamma ray. So write a balanced nuclear equation and then identify what the daughter nuclide must be. So let's start by putting the information in. We've got 13052 plus a neutron, so no charge, but it's going to add to the mass. So therefore, we're not actually going to change the number of protons, but we will increase the mass, giving it a different isotope, plus the gamma radiation being off. Now, we've got a mass number of 0 and an atomic number of -1 for the beta particle that's going to be given off. So this now decays, which means we get an increase in charge on our daughter nucleus, and therefore we can now check and look up 53 on the periodic table to show that that element, the new element that's been produced, will be an isotope of iodine.